Very important topic and definition, and this is all about generalized coordinate. So let's go for generalized coordinate. Why we need generalized coordinate, we will also discuss, and we will try to see that generalized coordinates are nothing but it is useful to understand the dynamics of a system. In spite of that, we have Cartesian coordinate system, which is a very nice coordinate system. But in spite of this Cartesian coordinate system, what we need some another type of coordinate system, some another type of our variables, such that we can easily identify the symmetry of a system, such that we can easily calculate the such that we can easily identify the motion of a system, and all this kind of thing can be easily justified. So let's go for what is generalized coordinate. So obviously, if again I am talking about generalized coordinate, then we have dynamical variable q1, q2 up to q1. So there are n number of dynamical variable. And what is generalized coordinate? So generalized coordinate is a dynamical variable which will justify independent motion of a system uniquely. So most important thing is that we have to define generalized coordinate, and we can define generalized coordinate with our convenience, that what we want to discuss, how and which type of motion we want to discuss. And in general, generalized coordinate is a dynamical variable, but it will justify independent motion. So what is meaning of independent motion? Meaning of independent motion, that generalized coordinate must be associated to the degree of freedom, because degree of freedom is nothing but all about independent motion. So this is one of the very interesting point, and it will justify motion of a system, independent motion, and motion of the system uniquely. Meaning of that, if we have one particular generalized coordinate, it will associated to one particular independent motion. Suppose it is associated to, let's say, radial part of motion, or let's say linear motion. And another generalized coordinate will not associated to this one. This should be associated to the another type of motion. So why we are saying it will justify independent motion of a system uniquely. And this definition is given by Landau. So this is very important definition, and we have to identify that which are our generalized coordinate in a very efficient way. In general, mathematically, you can choose anything your generalized coordinate, any dynamical variable, but that is not our case. We are doing physics, so we just want to solve, we want to take those generalized coordinate which are efficient. If I am talking about efficient in manner, that means I can identify more and more symmetry of a system. I can identify all possible motion of a system in a very nice way. So, and the most important thing is that if you have one particular system, why this generalized coordinate is different from our Cartesian coordinate system. If you have one particular coordinate system, suppose one particular system, then it is not necessary that all generalized coordinate you are using to define the independent motion have same dimension. In a Cartesian coordinate, all generalized coordinate have same dimension, but here it is not necessary. So it is very important thing. It is not necessary. It is not necessary that all generalized coordinate all generalized coordinate for a system have same dimension. Same dimension means it is not necessary that all generalized coordinate have dimension of length. It is not necessary. It will depends on your situation, and if you will surprise that sometime when we will go for the higher level of mechanics or some higher mathematics, when you will go for that, then what you will do, you will just choose the whole equation as your generalized coordinate. It may be possible that you can choose the whole bulky equation as your generalized coordinate, and then you can work with this. So generalized coordinate will always make your thing compact. But here at the master's level, at the graduation level, what we are doing, we are just sticking to ourselves to the motion. So r, theta, phi, angular velocity, angular thing can be only our generalized coordinate. But it may be possible that the whole equation, and this equation is nothing but the equation of momentum, and you can choose this as a generalized coordinate. And then you can define your generalized velocity. So it is a very generalized thing. So why we are saying it, that generalized coordinate can have any dimension. Any dimension, it is not necessary that it has dimension of length. It is not necessary, because it's a typical mathematical thing which will help us to understand different type of system, a different type of motion in a system. And obviously that motion must be independent motion. So what is the rule here? The rule is that number of generalized coordinate in a system must be equal to number of degree of freedom. So if you have 2 degree of freedom, then you have 2 generalized coordinate. And these 2 generalized coordinate will tell you about the 2 different story of a system independently and uniquely. This is very interesting thing. And now if we can define generalized coordinate, then we can also define generalized velocity. But before that, if you have any doubt, you can just ask me. Everyone is comfortable?
Yes, sir.
Okay. Good. So let's go for generalized velocity. Now, if Qi is generalized coordinate, then generalized velocity, GV, is nothing but generalized velocity. Generalized velocity corresponds to generalized coordinate Qi. Generalized coordinate Qi is Qi dot. And what is this Qi dot? Is nothing but dqi upon dt. So word conjugate is very important. You have generalized coordinate, and that conjugate, that corresponds. You have one velocity, and that velocity is identified as qi dot, and this is nothing but dqi upon dt. This is all about our generalized coordinate. Now, sorry, generalized velocity. And now we can have some very interesting observation now. Suppose, assume my generalized coordinate qi has dimension of momentum. My generalized coordinate has dimension of momentum. So let us assume we are just talking in a some system where I am assuming my generalized coordinate is momentum. Then what will be my generalized velocity? Then
Force.
generalized velocity is nothing but qi dot, and which is dp upon dt. Then I will identify force as my generalized coordinate, because rate of change of momentum is nothing but force. So what you will do? You will assume your momentum as your generalized coordinate, and then your force is identified your generalized velocity. And this is beauty, and this is all. You can just say, you have to just open your mind in a very broad sense when you are using the generalized coordinate. It is very different thing that at the master's level we are using that only r and theta, distance or angle, as my generalized coordinate. But as a theory, you can choose anything as your generalized coordinate if it is your dynamical variable. So it's a very interesting thing. Now, similarly, I can just say if my generalized coordinate is, let's say, angular momentum, then what will be my generalized velocity? Then my generalized velocity is qi dot is nothing but dl upon dt, and this is nothing but identified as torque, isn't it? Torque. So your torque can be your generalized velocity. And it's a very surprising thing, isn't it? That what is going to happen? Yes, we can use all this thing in a mathematics to solve the problem, to make it compact. We are using this kind of tricks such that we can easily solve the big equation, complicated equation, and make it very much simplified. Okay. But yes, in general, up to this level, up to master's level, when we are solving mechanics only, then obviously we will just go for either theta, or we will go for either a radius, or we will go for our length, this kind of generalized coordinate we have. Okay. So are you people comfortable up to this? Okay. So let's go for a 3 type of coordinate system. I think you know all these coordinate system, but we have to just revise it because it is very important for next classes. That in this coordinate system we can easily use this 3 coordinate system, mainly Cartesian coordinate, cylindrical coordinate, and a spherical coordinate. But in general, it may be possible that in a one particular system we have one generalized coordinate x and another generalized coordinate is theta. It may be possible, and obviously it has not any name. It will just come out with the geometrical calculation. So it's a very interesting thing. But yes, theoretically we have to use 3 basic coordinate system, and let's try to go for these coordinate system. So let's go for first Cartesian coordinate, which is very trivial, because unless until you don't define Cartesian coordinate system, you cannot define cylindrical coordinate system, you cannot define your spherical polar coordinate system. But yes, Cartesian coordinate system can independently define. Okay, so let's go for this. So we have to just go for coordinate systems. So let us try to go for a 3 type of coordinate system mainly. So we will go for coordinate system. Okay, so first we are talking about Cartesian coordinate. It is very simple and very trivial. What is Cartesian coordinate? We have basically your corner or room's corner is the best example of Cartesian coordinate system. You can have origin at the corner. This is my x-axis, this is my y-axis, and here is my z-axis. So this is the thing. So any point any point in Cartesian coordinate system can be represented by a position vector and whose x direction can be given as x, y, and z are the coordinate of this particular point. And you can write r is nothing but it is x I cap, y j cap, and z k cap. I cap, j cap, and k cap is uniquely defined. I cap will be unit vector in x direction, j cap in y direction, and z cap is and k cap in z direction. And obviously hence we have to go for the Lagrangian formulation. So we have to write the expression of kinetic energy. So what is my kinetic energy? My kinetic energy can be given by T, and this will be given by half m v dot v. V is nothing but my velocity. So when we can go for the velocity, we can write my velocity as x dot I cap, y dot j cap plus z dot k cap. And obviously, trivially, we can write my kinetic energy is all about half m, and we can have x dot square plus y dot square plus z dot square. Now, can you please tell me x dot, y dot, and z dot? These all have what? Same dimension. Meter per second, meter per second, meter per second. So in a Cartesian coordinate, x, y, z has same dimension. It is very trivial, very simple. We know all this stuff. That Cartesian coordinate, in the Cartesian coordinate, we have this is linear velocity. This is also linear velocity. This is also linear velocity. Obviously, hence we are talking about kinetic energy. Then obviously velocity square will be the leading term. So this is identification of kinetic energy. How you will identify this is the part of kinetic energy? Obviously, you will see generalized velocity square term will be there. And that is definition of your kinetic energy. Okay. So here my generalized coordinate x, y, z. Now, my question is that when you will use generalized coordinate as a Cartesian coordinate, which type of symmetry you want to discuss in a generalized coordinate? Which type of momentum you want to discuss in a generalized coordinate if you are using Cartesian coordinate system? Anyone?
Linear momentum.
Linear. Obviously, if you want to discuss the system in a linear symmetry, okay, symmetry, linear symmetry, then obviously Cartesian coordinate is useful coordinate system. Suppose some particle is moving along x-axis, then obviously Cartesian coordinate is the best one. But if some particle is rotating, then obviously Cartesian coordinate is not good one, because I want something which will give the sense of angle. And so we have to go for transformation of another coordinate system, and that is nothing but the geometrical transformation. So we have to go for that type of transformation. So second coordinate system is very interesting and very useful coordinate system that is identified as what? Cylindrical coordinate system. So let's go for cylindrical coordinate system. So if I am talking about cylindrical coordinate system, if I am talking about cylindrical coordinate system, then what are my dynamical variable? Then my dynamical variable is r, theta, and z. These are my dynamical variable, r, theta, and z, and we have to define what is my r, what is my theta, and what is my z. So how you will define this thing, and look at this thing is very important. Obviously, at this particular point of time, it's look just a very simple thing, very trivial thing. But when we will go for to calculate different type of problem, then you will see that, okay, it's take lot of energy to define which coordinate system and what is my r, what is my theta, and how I can directly write my equation into cylindrical coordinate system. It will take lot of energy and lot of effort. So try to understand all the coordinate system in a very nice manner. So obviously you cannot plot something like this is r, this is theta, this is z. No, you have to first plot your Cartesian coordinate system. Then only you can go for your cylindrical or other coordinate system. So if I am talking about cylindrical coordinate system, then obviously we have the symmetry of cylinder, isn't it? We have this particular symmetry of cylinder. So how you have symmetry of cylinder? You have one circle and then you have extend it in a z direction. So we can have this kind of symmetry. Let me make it in a nice way. And this is my x, this is my x-axis, this is y, and this will be my z-axis. Now, what is r here? This is very interesting. What is r here? So I will make it little bit bigger. So r is the radius of cylinder. You can have something, this kind of circular thing. Okay. So let me make it little bit more beautiful. So this is my, and you have this kind of situation. This kind of situation is there. These all are parallel. So this is my x-axis, this is my y-axis, and this middle is my z-axis. So what is my r? It is very interesting. This will tell you all about the radius of cylinder. So you can measure this value as your r. Okay, this value you can have everywhere, this parallel x and y. Let's say this is x, this is y, this is z. This is your r. This is r. So your r is measured from z-axis actually. This is very interesting. This is your r. This is radial direction. This is your r. Okay, this is your r. This is your r. Okay, so one radial part. So this is radius. This is measured from z-axis. This is your r. Okay, and this angle, this r is making angle with x-axis is theta in general. Okay, so this is your r. This distance is your r, and this angle making with the x-axis is theta. So we have r, theta, and one particular the distance in the z direction is z. So suppose you have at this point, your particle is at this point. So what you will do? You will just make a circle and you have this particular, and suppose your particle, I am just taking this particle at here. Suppose at the surface of cylinder. So this will be your r. And obviously it will make angle theta here. And obviously this height is z. This height is z. So it's a very interesting coordinate system. You have three variable. One is radial variable, that is radius, just away from the z-axis, just away from the z-axis. And this r is making angle theta with x-axis. So can I write what will be my x? X can be written as r cos theta, isn't it? You can take the angle with respect, you can take the component towards x is nothing but r cos theta. Similarly, what is your y? Y is nothing but r sin theta. And what is your z? Z is nothing but exactly same z we are using into the Cartesian coordinate system. And now we have to calculate what are the velocity. What is, by the way, what is generalized coordinate here? What is generalized coordinate here? The generalized coordinate is r, theta, and z. Any point can be written as a coordinate r, theta, and z. So what will be my generalized velocity here? The generalized velocity is r dot, theta dot, z dot. This is your generalized velocity. And now I can easily calculate what is my x dot. X dot is nothing but total derivative with respect to time. So then we have to first go for, and this is equivalent to r dot cos theta plus r, and this will be r minus sine theta, theta dot. So x dot is equivalent to r dot cos theta minus r sine theta, theta dot. What is r dot? R dot is nothing but dr upon dt. Yes. And similarly, we can go for y dot. What is y dot? R dot sine theta plus r cos theta, theta dot. So this is your y dot, and similarly we have z dot, and z dot is nothing but z dot. Now we can go for writing the our basically kinetic energy or in the cylindrical coordinate. So what is kinetic energy? We have defined my kinetic energy is half m x dot square y dot square plus z dot square. Now we have to go for x dot square plus y dot square. Look at, we can calculate from here. So I can say this is A, this is B, this is C, and this is D. So x dot square plus y dot square is equal to what? First, x dot square means what? A square plus B square minus 2AB. You can just see this thing, isn't it? A square plus B square minus 2AB. What is y dot square? C square plus D square plus 2CD. Now, if I am just writing x dot square plus y dot square, then obviously we can collect A square plus C square. So what will be left out? I can take r dot common, then cos square theta plus sin square theta is 1. So first part will be, you have half m r dot square. Second, you have to go for b square plus d square. So what will be your b square plus d square? Just tell me.
R square.
R square theta dot square. You can take common, and cos square theta plus sin square theta, or sin square theta plus cos square theta is 1. So you have r theta r square theta dot square. And obviously the cross term 2ab and 2cd, you can just see what will happen to 2ab and 2cd. Is that same thing? R dot is there, theta dot is there, cos theta, sin theta, r. But one side it is minus, another side it is plus. So what will happen? This term will be 0. So cross term will be cancel out each other, and we have this, and again z dot is equal to nothing but z dot. Now look at here. What is r dot? What is r dot actually?
dr by dt.
Dr upon dt, but this is in which direction? This is in r cap direction, isn't it? This is in r cap direction. And what is direction of r theta dot? What is direction of r theta dot? That is obviously in tangential direction. Okay, this is direction of r theta dot. Tangential velocity is r theta dot. And what is direction of z dot? Z dot is obviously in this direction. Z dot in this direction. Now, what is direction of theta dot? What is direction of theta dot? Anybody?
Angular
आराम से. What is direction of theta dot? Jitendra, can you tell me what is direction of theta dot?
It will be either clockwise or anti-clockwise.
No, please. Theta dot. What is direction of theta dot?
It will be vertically. What?
Tej Kumar, what is direction of theta dot?
Vertically upward.
Vertically upward. Okay. So that means, sorry. theta dot has direction in z cap direction. Okay, this will be in z cap direction. R theta dot is in tangential direction, please. But theta dot in z cap direction. Are you getting my point? This will be in z cap direction. So angular velocity omega is in z cap direction. This is very interesting thing. You have to remember this particular thing. What is r dot? This is in radial direction. Okay. R theta dot in the tangential direction. Z dot in z cap direction. And what about theta dot? This is also in z cap direction. The angular velocity. Okay. V is equal to r cross omega. And then only you have the direction of theta dot is in z cap direction. And now look at here. R dot has dimension of meter per second. What is dimension of r theta dot? What is dimension of r theta dot? Anyone?
Same, sir.
Same thing, meter per second. What is direction of z dot? Meter per second. But what is your generalized coordinate? Your generalized coordinate is not r theta dot. Your generalized coordinate is r, theta, and z. So your generalized velocity is r dot, theta dot, and z dot. What is dimension of r dot? The dimension of r dot is meter per second. And what is dimension of theta dot? That is nothing but radian per second. And what is dimension of z dot is also meter per second. So now you can see in the Cartesian coordinate, all generalized velocity have same dimension. But here, if we have changing our coordinate system, then we have seen that, okay, the dimension of r dot and theta dot is different. And this theta dot will tell you all about the angular symmetry. When something is rotating in some plane, then obviously this theta dot will help you to understand that kind of symmetry. And you will see that angular momentum is associated to this particular theta dot. Radial momentum is associated with this r dot. And this z dot will tell you about the linear momentum along z direction. So it's a very important thing that why you are using this particular symmetry. Is that every problem can be solved into every symmetry? Mathematically, yes, but physically you cannot conclude the thing. We will see when we will go for the conservation of angular momentum and all kind of system here. Up to that, everyone is comfortable?
Yes, sir.
Okay. So let's go for next very important coordinate system is nothing but spherical polar coordinate system. So for the spherical polar coordinate system, spherical polar coordinate system. So what is my variable? R, theta, and phi. There are two angular variable, one is radial. But this r and another r in the cylindrical coordinate is different. So now how you can assume, how you can define all these things. So this is again my x, y, z. So you have universally defined your x, y, z. And let's say there is any point on a space. This point is in a space. And this distance from origin is r. Okay. This distance from origin is r. And you can say this point is r, theta, and phi. Now, what is angle theta? Angle theta is made with the z axis. So this is your angle theta. So one component of R along Z axis is what? बताइए क्या होगा? The component of
R cos
R
theta.
along Z axis is what? R cos theta?
R cos theta.
Yes. So this will be R cos theta. Now, what will be the another component? R sin
R
theta?
sin theta.
So where is this R sin theta? Where is this R sin theta? Parallel to Y
Position
axis?
and XY plane.
Huh? Parallel to Y axis? No, this is not parallel to Y axis. Assume,
No, sir. No, sir.
so
XY
suppose you
plane.
have, wait. Now look at here. You can assume this is my Z axis. Okay. And this is your R. So this is your R cos theta. This is your R cos theta. But R sin theta is in my palm, isn't it?
Yes, sir.
It is in my palm. So it is in XY plane. So next component, the projection of R in XY plane is given by this distance, and this distance is nothing but R sin theta. This is your R sin theta. And what is your angle phi? This R sin theta will make angle phi with x-axis. This will make angle phi with x-axis. And this is the same angle which can move about z-axis. This is the same angle which will move about z-axis. This theta is moving away from z-axis, and this phi is moving about z-axis. So you have to always keep in mind this particular thing. Now, can I say x is equal to nothing, but I have to take the component of R sin theta along x-axis. That will be R sin theta cos phi, and y is equal to nothing but R sin theta sin phi. Okay, I am just giving you homework. Just do it with yourself for the practice. Okay, and just find what is your kinetic energy. Your kinetic energy is half m r dot square r square theta dot square plus r square sin square theta phi dot square. So this is your homework. Just try to find z dot, x dot, y dot, take it to square and try to prove this particular thing as your homework. So you can do it with yourself just for the practice. Now, what are here your generalized velocity? There are three generalized velocity. The first generalized velocity is r dot. So this is in radial direction. This is in radial direction r dot. Another is what? Theta dot. And another is what? Phi dot. Phi dot will tell you all about the rotation, this rotation, azimuthal rotation. There can be two types of rotation. Your particle can rotate about z-axis and it can rotate away from z-axis. So this angle will tell you about the direction of theta. And this rotation will tell you about the direction of phi dot. So this is the exactly in the same direction phi dot in the z cap direction. Okay, so this is very interesting. And now if you have this type of situation, suppose there is one linear symmetry and there are two angular symmetry, and you can just move either here or something like this, you have to use this spherical polar coordinate system. So it is very important coordinate system. Suppose you are in the cone, you can write it in a cylindrical coordinate, you can write it into a spherical coordinate, but you have to decide which coordinate system for a cone is important. So whatever we have discussed, let us try to analyze it with one particular problem. That how we can use this coordinate transformation to this particular problem. Up to that, everyone is comfortable?
Yes, sir.
Okay. So let's go for one problem. Again, I am taking the degree of freedom in this contest because we have to solve mechanics. and then we will just try to see which coordinate system is more efficient and how we can use different coordinate system to just identify the system, just identify the motion of a system. So let's go for one very nice problem. Obviously, we have to solve all this thing, whatever we have discussed into last class as well as today's class. So what do we have? We have one cone. Okay. And this cone is making half angle alpha. X, Y, and let's say this is my Z. So now my problem is that a particle is constrained to move on a surface of cone. A particle is constrained to move on a surface of cone, on an inner surface of cone. Okay, inner surface of cone. Now, the first question is that write down equation of constraint in Cartesian coordinate, B cylindrical coordinate, and C spherical coordinate. Okay, you have to write the equation of constraint in all three coordinate system. Now, your particle, how you will write the story? Now just tell me what is constraint here? What is constraint here? Mridul, can you please tell me what is constraint here? बोलिए।
Particle remains attached with the cone.
मैं जिसे पूछ रहा हूं वो बताएंगे, है ना, तो बेटर हो पाएगा। मृदुल, कैन यू प्लीज टेल मी व्हाट इज कंस्ट्रेंट हियर?
So that the particle have to move on the surface of cone.
Very good. So particle will have to move on a surface of cone. So you have to just say in a English language. Can you make it mathematical? क्या आप मैथमेटिक्स में से बोल सकते हो? Just tell me in a mathematical language. Saina, can you please tell me if she is saying that particle is moving in an inner surface of cone with half angle alpha, what is mathematical meaning of that? How mathematically we can analyze? How mathematically we can think? बोलो, yes.
Sin x.
Just try. देखो जब तक ट्राई नहीं करोगे नहीं होगा, है ना? Just try it.
That cos alpha.
Okay, that means you want to say that this particle will always make a constant angle with z-axis, isn't it?
Yes.
Okay, so obviously we can write angle in term of sin alpha, cos alpha, or tan alpha, anything we can write, isn't it? So चलो मैं tan alpha लिखता हूं. So let's try to write tan alpha. So what is tan alpha? So tan alpha is this distance by this distance, and we have to use Cartesian coordinate. So what is Cartesian coordinate here? X, Y, Z. Suppose we are writing tan alpha for all Cartesian coordinate, cylindrical coordinate, and spherical coordinate. Chalo, batao to what is tan alpha? Obviously, this distance by this distance. Yes. So what is this distance? Obviously, this distance is nothing but Z. So I am 100% agreed. This distance is Z. What is this distance? What is this distance? Anyone?
Y.
Why? Now look at here. You have to understand the symmetry. This is not y. It can be here also. 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 Isn't it? If you will see the symmetry of cone, this particle can be here also, but it looks just like y. So what will be this distance? What will be this distance?
Radius.
Radius. But you have to write it into Cartesian coordinate x and y. You cannot use r here.
Sir, under the root x square plus y square.
Very good. So what will be this? So this will be nothing but x square plus y square. This will be your equation of constraint into Cartesian coordinate. Now, and in the Cartesian coordinate, I have to use x, y, and z. And we have used this thing. Now, let's go for cylindrical coordinate. What is tan alpha into cylindrical coordinate? Can you please tell me? Again, this z will be remain z. So this z will be there because here we have to go for r, theta, and z, isn't it? And what is this term into the cylindrical coordinate? What is this term?
R.
R. That term is R actually, because this is your radius of cylinder. This is radius cylinder. This is your radius of cylinder. This is radius of cylinder. So here we are using tan alpha is equal to R upon Z. And you can also verify with also. How you can verify? You can just write x is equal to R cos theta and y is equal to R sin theta. And then x square plus y square is equal to R root under R square, that is R by Z. So this is into the cylindrical coordinate. Now just tell me into the spherical polar coordinate. How you will write this tan alpha? What is a spherical polar coordinate? What are variables into a spherical polar coordinate? R, theta, and phi. By the way, what is theta? What is theta? Theta is the angle made by the z-axis, isn't it? Theta is the angle made by z-axis. So how much angle it is making by the z-axis? Alpha.
Alpha.
Alpha angle is making with the z-axis. So in a spherical polar coordinate, we can easily write theta is equal to alpha. In a very simple way, we can write theta is equal to alpha. If you want to verify, you can easily verify. How you can verify? You have x is equal to R sin theta cos phi, y is equal to R sin theta sin phi, and z is equal to R cos theta. So x square plus y square is equal to R square sin square theta root under. So that will be, you have tan alpha is equal to R sin theta denominator, because x square plus y square, cos square phi plus sin square phi is 1, and by R cos theta. Z is equal to R cos theta, and you have tan alpha is equal to tan theta. That means alpha is equal to theta. But if we understand symmetry, we can easily say, okay, this angle is nothing but in a spherical polar coordinate, this angle is alpha, and which is actually variable theta. So my theta is a constant value. That is your alpha angle are there. So theta is equal to alpha is the constraint. Now, can you please tell me which coordinate system you prefer to solve the problem? What will be your first choice? What will be your second, and which coordinate system you will not going to choose here? Anyone? Just look at this equation of constraint. Here you can see, Here equation of constraint involve all three coordinate system, x, y as well as z. And here we are using only two coordinate system. And here we are using only one coordinate to define my equation of constraint. And you will find that easiest to solve this problem into a spherical polar coordinate. After then you have little bit toughness into cylindrical, but in the Cartesian coordinate system, it is next to impossible that you can solve in a proper way. It is very difficult because its symmetry can be visualized much better into the spherical polar coordinate. After then, it can be much better visualized into the cylindrical coordinate system. And what will be degree of freedom? And the degree of freedom here will be, obviously, you have 3 into 1 minus 1, only one coordinate. So at a time, you will use only one coordinate system. So obviously, 1 is my equation of constraint, that is tan alpha is this one, or in cylindrical coordinate tan alpha is this one, or a spherical coordinate tan alpha is equal to tan theta. So that means you have 2 degree of freedom. And if you have 2 degree of freedom, that means you need 2 generalized coordinate to solve this problem. And 2 degree of freedom can be identified as one is rotating, independently it can rotate, and another independently it can go downward. And if you will mix these two things, then obviously the motion of this particle will be go downward, something like moving in a spiral thing. Yes, and if you are changing r in the cylindrical coordinate, you can see r and z is dependent to each other. So either you will choose r or z, and another will be your angle theta. In the spherical polar coordinate, theta is equal to alpha. So then you have to avoid theta. You will just go for r and phi as your generalized coordinate. But in this thing, it will be very havoc to solve the problem. I think you have little bit glimpse on this particular why we need coordinate transformation. And you will see from the equation of constraint, we can identify which coordinate system we have to use in a very proper way and in a very nice way. So up to that, if you have any doubt, please let me know. Any doubt, any question? Everyone is comfortable? Sautan, are you feeling okay?
Yes, sir.
Mahima, are you comfortable?
Yes, sir.
Okay, good. So obviously, these are the prerequisite for solving the problem. Prerequisite means before going to Lagrangian formulation, we have to understand all these things at least. Okay, so just go and revise this thing. Okay, and in the next class, we will start to formulation of Lagrangian. We will start with the Hamilton's principle, but before that, we will do little bit of calculus of variation, because Hamilton principle is nothing but the outcome of calculus of variation. Okay, so I think we should stop here. It's okay.